Today we're going to introduce Ohm's law and take a deeper dive into the concept of voltage in electric circuits. We'll use Ohm's law to calculate the current in a circuit and then build various circuits to verify it's true. We'll then take a look at various different kinds of voltage sources, including many types and sizes of batteries. By building various circuits, we'll answer the question, why do we have so many different sizes of batteries with similar voltages? And finally, we'll wrap up by discussing the concept of AC versus DC current in electric circuits. Hello, welcome back. Today we're going to have an introduction to Ohm's law and also a deeper look into voltage. These two concepts are absolutely essential to do anything in circuits. That's what we're going to conquer today. I want to start out with a question. This is a large battery. Some of you may or may not have ever had occasion to use. It's 6 volts. 6 volts, that's the voltage for this battery. All right. This is a D size cell. It's a 1.5 volt cell, right? This is a C size cell. You can see the difference. It's also 1.5 volts. You see the pattern here? This is a double A cell, 1.5 volts. This is 4 of these, what we call triple A cells, each of these 1.5 volts. And these little bitty guys, these little tiny little flat batteries, 3 volts each. So if I put 2 of these 3 volts batteries together, I can get 6 volts, which is the same voltage as this. If I know that each one of these batteries is 1.5 volts, if I stack them in the right way, I can add up to 6 volts, the same voltage as this. Why do we have so many different size batteries that they're really are the same voltage? If this is 6 volts and this is 6 volts, what is the difference between these two batteries? So in order to answer this today, we're going to have to talk about the difference between theory and reality. In theory, we have what we call Ohm's law. It's the most fundamental equation and law that you have to master in order to understand electricity, but we're going to apply it, understand what a deeper look into voltage using Ohm's law, and then we're going to use it to try to understand the difference in these voltage sources. So this lesson is all about voltage sources, trying to understand voltage a little bit deeper. Let's get started right now. So let's jump right in by diving into Ohm's law. We're going to talk about Ohm's law a lot, but I need to introduce it here in order for us to make any progress at all. Ohm's law is a very simple algebraic equation. The 3 variables of interest are voltage, current, and resistance, which we've talked about in the past, and Ohm's law states that the voltage across any passive circuit element, I'm going to talk about what a passive element means in just a second, the voltage across it is equal to the current passing through, the electric current passing through that object multiplied by its resistance. Now this applies right now we're going to basically be talking about resistances. We have to modify it a little bit when we talk later about capacitors and inductors, and we have to totally change the discussion completely when we get to nonlinear components, which are diodes and transistors. We have to kind of modify things later. But for now, I want you to discuss Ohm's law with me in the context of only resistors. We have to learn resistors first. It's the easiest thing to understand. Now, if the voltage across a resistor is equal to the current flowing through the resistor times its resistance, this is an algebraic equation that you can solve for whatever variable you'd like. Another common way, or a very useful way to write it, is that the current at I is equal to V over R. Just take this equation, divide both sides by R, and you'll be left with I is equal to V over R, which is what we have here. These two forms of Ohm's law are what you will typically see in books, and they're exactly the same. It's not that one is better than the other, it's just like 2 sides of the same coin. It represents the same exact relation. All right, now, we mentioned in the introductory lesson that we have voltage, current, and resistance, but we need to solidify it more. What does voltage mean? Voltage is the push in an electric circuit. This battery is providing a physical push to the electrons in the circuit. The push is coming from a chemical reaction. Ultimately, the push comes from what we call the electric field. You know from basic science, 2 electrons repel each other. Like charges repel, either 2 protons or 2 electrons, they repel, and opposites attract. That electric force ultimately is where all electricity, the force to push the electricity comes from. It comes from the electric force. In a battery, it's coming from the chemical reaction that's wanting to push electrons out of the terminals and back around to the other side. We'll talk a little more about batteries a whole lot in just a second. But of course, we have electricity that's generated by nuclear power and other means They're all generated various ways, but ultimately the voltage that comes out is the push. How much push do you have that's causing the electricity to flow? So when we talk about voltage, I want you to always replace it with the word push in your mind. If I can make this correct, push. It's the push, right? The electric current itself is what is actually flowing. It's what we call the flow. We're going to talk about the definition of current very soon. It's literally how many electrons per second are flowing past a point. It's literally like the water flowing in a river, whereas the voltage is maybe the height of a mountain. When we talk about voltage, I want you to picture a mountain. You're standing on the mountaintop and you can throw rocks off the mountaintop because you're at a high potential. We call it potential energy above the ground in physics. When you throw the rock, it accelerates down the side of the mountain. When it gets to the bottom of the mountain, it has no more potential anymore, so it eventually stops rolling, right? When you have a battery, you're at the top of the mountain, and it's pushing the electrons. But when they get it back around to the other side, when they go out of one terminal and get back around going to the other side, then they have lost all of their potential energy, and then they go back into the battery to be accelerated and pushed out the other side again. So it's very much like a mountain. The higher you are above the ground, the more potential you have to do work, the higher the voltage in a battery. So voltage is push at the top of the mountain. What is flowing is the actual electric current. And if there are any obstacles in the way, or resistors in this case, we call it the resistor, the resistance R, okay? Now, I want you to remember, we're going to go over units again. Voltage, the voltage is in volts, of course. The current is I. You can use capital or lowercase I. And the resistance we usually call R. So V equals IR, that's these three variables right here. Now, the base units of voltage are volts, but of course, we might instead talk of millivolts. That's 1/1000th of a volt. We might talk about kilovolts, which is thousands of volts, but it's just a modification of the basic unit of a volt. Same thing for current. We might have the base unit of current is called the ampere, which we abbreviate A, but we might instead talk about milliamps, which is thousandths of an amp. Right? We might talk about microamps, which is millions of an amp, and we might talk about kiloamps, which is like thousands of an amp. Right? In terms of resistance, we might talk about ohms. We use the symbol omega for ohms, but we might modify it. We might talk about milliohms. We might talk about microohms and nanoohms and so on, but it's more common to talk about kiloohms or even megaohms. All right, now this is all stuff we've talked about in the past, but it bears repeating because you have to understand the definitions. When we talk about a circuit, if somebody tells you, hey, that circuit has 1,000,000 volts of electricity flowing through you, you know that this person does not know what they're talking about because voltage does not flow. What do we say flows? The current flows. The current is the only thing that flows. It's literally the electric flow of charges in a closed path. The current flows, but the push required to start the flow or to continue the flow is the voltage. And if there are any resistors in the way, it tends to reduce the amount of current. That's why it's called the resistance. All right. And the interplay between these three variables we call Ohm's law. Now we want to learn about all of these things in practical detail. We want to build some circuits. So let's take a theoretical circuit, the absolute simplest circuit that I could possibly think of, right? We're going to have a voltage source. There's many symbols for a voltage source. I'm going to write it like this, plus, minus. And we're going to say that this voltage source is connected directly in the path with a resistor. This is a symbol for a resistor. And in this case, I'm going to say that this voltage has a voltage of 1 volt, and the resistance has a resistance of 10 ohms. Now I want to ask you, if I take a 1 volt source and I connect it directly in the path with a single element, which is a 10 ohm resistor, how much electric current will flow? We know that there will be current flowing here, going around back to the other side. Remember, we know the electrons are coming out of the negative side. We know that, but we talked about in the last lesson that algebraically, since electrons are negative and they are coming out this side, mathematically it's the same thing as talking about the opposite current we call the whole current coming out of the positive side and going this way. Now, I don't care personally what you do, but when you take electrical engineering classes, we always talk about the positive current flow. It makes the equation simpler because there are no negative signs. But if you want to think about electron flow, that's fine. I'm just telling you that they're mathematically the same thing.
It's like, positive 3 is the same as negative 3. Put two negatives together, you still get a positive 3. You can write it different ways, but it's the same thing, all right? So this is our circuit. How do we determine the current flow? We go up to Ohm's law. You can use either form you want, but we're trying to find the current, so we can say that I is equal to V over R. But we know that the voltage across this resistance is 1 volt. And we know that this resistance is 10 ohms. Now we're working in the base units. We know that the base units are voltage in volts, and then amps is the base unit, and ohms is the base unit of resistance. So if I know I've put a unit of volts in here, and I know I've put a base unit of ohms here, then I know that the current I calculate is going to be in the base unit of amps. All right, so what's 1 over 10? It's 1/10 or 0.1 amps. So what we expect is if we connect a 1 volt source directly across a 10 ohm resistor, that there should be a current flow of 0.1 amps, which is 1/10 of an amp. So here is where we have to go from theory to reality. In reality, you're not going to be able to get exactly what you write down on the board because your voltage source is not going to be exactly at 1 volt. Your resistance is not going to be exactly at 10 ohms. And the measurement apparatus, whatever measurement apparatus you're going to use, an ohm meter or voltmeter or whatever, is not going to be infinitely accurate. But you should still be able to convince yourself that you're getting something close enough to this that we're representing reality. So what we're going to do, we're not going to use batteries yet. We're going to use my voltage source right here, and we're going to connect it across this resistor. Now this resistor is a physically large resistor. In the last lesson, I worked with resistors that were very, very small. We're going to have a whole lesson on resistors and resistance very soon. But just know that the reason I'm using this very large resistor physically, notice it says 10 ohms printed on here, and it says 10 watts. The W is watt. We haven't talked about power yet, but this resistor is physically large so that it can absorb a lot of heat without burning itself up. I wanted to use a large one because I don't want to burn up my resistors teaching you these concepts. But the larger the resistance, the larger physically the resistor is, in general, the more power that it can take, the more heat it can dissipate without burning itself out. All right, so what we're going to do is connect one side. These are coming straight out of my power supply over here, which I can control very carefully. In a minute, we'll be using batteries, but right now I want to use my digital source here. And so all we have is literally a single circuit element, a single resistor coming straight connected to our voltage source. Now I want to dial this thing up so that it goes up to 1 volt. So I will increase the voltage from my source here. Whoops, I'm turning the wrong knob. I will increase my voltage source and try to get it, I'm going to use the fine knob to get it as close as I can to 1 volt. Right now it's 1.01 volt. There's 1.00 volts. So we said when there was 1 volt across a 10 ohm resistor, we should get 0.1 amps. And notice that we have 0.104 amps. So this is what I'm saying. It's not exactly 0.1 amps, but that's just because there's a little play in the knob here. There's a little bit of inaccuracy in the display. There's a little bit of resistance in the wires connecting everything together. And also this resistor is not exactly a 10 ohm resistor. But notice that we get exactly what we predict, 0.1 amps. Let's just, for giggles, disconnect it from here. I'll turn my voltage down, and I'm going to turn my meter on over here. This is you can measure voltage, you can measure current, and so on with this. And just for giggles, let's go ahead and measure the resistance of this resistor here. So all I'll do is I'll connect to each side here, and we'll measure and see what it says. We'll give a nice good contact pressure and see what it comes up with. And we see right here 10.2 ohms. So it's not exactly 10 ohms. That's one thing I told you. The resistor has a certain tolerance to it. They can't make them infinitely accurate, okay? And also, when I touch the resistor with these probe tips, that introduces a little contact resistance as well. So in the real world with circuits, you calculate based on your desired values, but you know in real life, the real values will be a little bit different than what you calculate just because in the real world, it's not perfect. All right, so let's go back and let's reconnect. I got my voltage all the way down, so I'll reconnect my circuit here. So we verified that when we put 1 volt across this, we got the 0.1 amps out. So that's correct. Ohm's law is validated, right? Now what we're going to do is play with this a little bit more, right? So we're going to go up to 2 volts. So what if I put 2 volts across this? So I change the 1 volt to 2 volts. I can erase this if you want and put a 2 there. But if I put this and replaced it with 2 volts, it would be I is equal to V over R, but the voltage would now be 2 volts, and the resistance would still be 10 ohms. So I'm working in the base units of voltage and amps. And so what I'm going to get is the current, in this case, 2 over 10, is going to get me 0.2 amps. Now let's go over here and see if that's what we get. We haven't changed anything. We're going to now increase this thing to, instead of 1 volt, we're going to go up to 2 volts, and I've overshot, so I'm going to go down. It's kind of hard to get it exact, so I'm going to try to go very, very slow, and it looks like I've overshot again. So I'm going to go down, and I'm going to use the fine knob to go up to 2 volts. What do I get? 0.204 volts. Again, I mean amps. Again, not exact, but it's close enough that we know that what we're predicting with Ohm's law is matching reality. This is a nice device because this voltage source also tells me how much current is flowing. I could use this meter to, of course, hook into the circuit and measure the same thing, but it's just too easy to use the source that I have. All right, so let me turn it off. I don't want to dissipate any power for no reason. Let's predict what's going to happen. Let's do a couple more. Let's say it's 3 volts. I is equal to V over R. Let's say I change this thing to 3 volts. So 3 volts and 10 ohms. So 3 over 10 is 0.3 amps. And we're going to check that. We know that this one's correct. And I'm going to go ahead and calculate the last one again. I'm working my way up to 6 volts because, remember, I have this 6-volt battery. I'm going to start playing around with this 6-volt battery soon. So I want to show you what happens when we get up to 6 volts. So when I use the battery, we'll see the difference, right? If there is a difference. So let's change it from 3 volts to 6 volts and 10 ohms. And so what do you get? 6 over 10, 0.6 amps. So we have 2 of them to check, 3 volts and 6 volts, and let's just see what we get. So we'll go up to 3 volts, and I've overshot, so I'll go down, very, very close, and I'll go 3. So at 3 volts, I get 0.302 amps. So according to Ohm's law, that's what I predicted. That's correct. And then I'm going to go up to 6 volts. There's 5 volts, and there's 6.06. So I'm going to go down a little bit right here with the fine knob. I'm going to go down to 6 volts. What do I get? 0.583, right? Which is very, very close if you round it up to this. Now you have to ask yourself, oh, why is it different? What's wrong with that? What am I doing wrong? Well, this wire is not a perfect resistor, right? So this is the difference between theory and reality. It's not a perfect conductor. This wire, even though it's made of copper, actually has a very small resistance. Also, notice I'm connecting these things with these alligator clips, so there's a little contact resistance where they connect, and also, you can't see it off the camera, but I have another connection point from the power supply to these wires. There's another contact point. The higher and higher I go with the voltage, these little imperfections are going to be magnified a little more. So at 3 volts, it was pretty close to very close to accurate, 0.3 amps. When I get to 4 volts, let's go down to 4 volts. We expect 0.4, let me go up just a little bit. We expect 0.4 amps. Notice it's very close, but not quite. Then when I get to 5 volts, it's a little bit different, right? You can see the difference there. And when I get it at 6 volts, it starts to be amplified enough where it's different here. Okay, 0.584 amps. So, but we still know that as we increase the voltage, the electric current in the circuit seems to go up by not by an equal amount, but by a proportional amount. The reason I'm doing this is to show you that when we have linear components in the circuit, and what I mean by linear components basically is, in this case, resistors. We'll talk about capacitors and inductors later, but we have nonlinear components. We're going to talk about later diodes and transistors that amplify things. Those are nonlinear components. The current and the voltage relationship in a transistor is not linear like this. In this case, when I started over here, when I started at 1 volt, I got 0.1 amps. 2 volts, 0.2 amps. 3 volts, 0.3 amps. 6 volts, 0.6 amps. Even though it wasn't exactly, matching because of reality, we know that matches the theory, right? Every time we increase the voltage by the same amount, the current increased by the same constant amount. We increased by 1 volt, 1 volt, 1 volt, 1 volt, and then we go from here, that's 0.1 amp, then another 0.1 amp, then another, from here to here, 0.3 amps. Actually went 3 volts and we increased 0.3 amps. So they increase with lockstep from one another. The current and the voltage through a linear element like this increases linearly. As you increase the voltage, the current goes up by a proportional amount, right? And the reason it's like that is because if you go back and look at Ohm's law, I is equal to V over R. This relationship is a linear relationship. What do I mean by a linear relationship? Remember back to algebra class, right? In high school, you spent a lot of time, everyone spends a lot of time graphing lines. We say this is an equation of a line. What does the equation of a line look like? Right? Y equals m times x plus b. And you learn in algebra class that this is the thing called the y-intercept, and this is the thing called the slope, and this slope tells you how steep the graph is. But basically, if you can put any equation into this form, you know it's going to form a straight line. We call that a linear relationship. But what is Ohm's law? I equals V over R. If I say that I is equal to V over R, you say, well, wait a minute, that doesn't look like that. But then you say, okay, notice that the resistor was constant. That never changed. All I changed was the voltage, and I measured the current. So I can write this as, instead of like this, I can write this as 1 over R multiplied by V. Think about how we multiply fractions. If I make this V over 1, then you have V multiply, you get a V on the top and an R on the bottom. So I don't need to write it like that. I can just leave it like this. But then what happens if I say, okay, I'll just change the y-intercept to be 0. Then this equation, the equation for the current through a resistor, is a line. And it's a line because we can then say that the slope of this line is just 1 over the resistance. If you think of it that way, that this is just a constant, right? Because the resistor was 10 ohms. So this is just a constant number, 1 over 10, right? And this is the slope of the line. Then it's I equals mx plus b, where the y-intercept is 0, and the reason it's 0 is because when you drive it with 0 voltage, you get 0 current. So of course the line has to go through the origin, because if you don't put any voltage in, you don't get anything out. That just means the line goes through the origin. So I don't want to graph it and draw it, but you get the idea. I just wanted to show you that it behaves linearly because Ohm's law is the equation of a line. That's all I wanted to get across to you so that you understand it. And just as a preview, when we get to transistors and diodes later, the current voltage relationship will not be a line. It will be a non-linear type of deal because of the way those devices are constructed. And because of that, you can amplify things. That's one of the main uses for transistors. We'll get to that much, much later. All right, now we need to transition ourselves to talking about the batteries. Why do we have all these different size batteries if they're all about the similar voltage range? All right, now, I told you to take my word for it earlier. Now I want to actually show you. This is a 6-volt battery. It's printed right on the side here. And if I connect my voltmeter across the 2 terminals and measure the voltage, I get a negative because I've got them flipped around. If you look over there, it's 6.427 volts, right? Now this is a 6-volt battery. This is another theory versus reality thing. It's printed on here that this is a 6-volt battery, but when it's fully charged like this, it's a little bit more than 6 volts. As it is depleted, that voltage is going to come down and down and down, but usually these things are about a little bit more than their stated voltage when they're fresh out of the box like this. So this is what we would call a 6-volt battery, even though it's a little bit more than that. Now let's go downstream a little bit. We'll put the 6-volt battery off to the side, and I want to talk to you about these things. These are called D-size batteries or D-cell batteries. I'm going to take one of them out, right? If you read the fine print on this thing, it says that it's 1.5 volts. Let's see. So what I will do is I will connect my meter across the top like this. And again, notice it's not 1.5 volts. That's what's printed. It's a little bit more than that because it's fully charged. Now, if you take 2 of these things and you connect them, you got to, again, think about voltage as a mountain. This literally represents like the top of a mountain, right? And you're at the high part of the mountain when you're talking about the top terminal compared to the bottom. If you stick 2 of them together, it's like stacking 2 mountains on top of each other. So what do you think the voltage should be if I've got them stacked like this? Well, it should be adding the 2 together because it's literally like stacking 2 mountains, one on top of another. And if I look over there, the 1.6 plus the 1.6 is 3.2. So that's exactly what we get. So when you see these little devices like this, these little battery holders like this, all that's going on is it's alternating the direction, but all that's happening is you're putting them end to end to end to end like this. So if I put the flat part on the spring right here, and then the flat part on the spring right here, like this, and then these are oriented the same way. All I've done is instead of stretching them out in a line, I've folded them up, but they're still end to end like this. So if I take a look at this, then I know it's about 1.5 times 4, so it should be about 6 volts. Let's see what the actual voltage is. So I'm going to hold this side of the wire right here, and then the red side, I'm going to hold with this one right here, and we'll read the meter over there. 6.5 volts is what I get here. For reference, remember that this one was about the same, 6.4. So the question I have for you, and that what we're going to answer is, if this is about 6 volts and this is about 6 volts, why do we have these different size batteries, right? Let's go through the different sizes I have. I'm going to give you the punchline and tell you why we have them, and then we're going to do a little experiment to show you why what I'm telling you is correct. All right, so let's put these away. These are the D cell batteries. Now these are the C cell batteries. If you read the package on these very carefully, this package will also say that each of these batteries is about 1.5 volts. So once they're end to end like this, same kind of deal, I'm going to hold it like this. Again, you're going to get just a little bit over 6 volts. Notice they're all coming out to about 6.4 volts once you stack them together. These are called AA batteries. If you read the package, each one is 1.5 volts. What do you think we're going to get if we stack them together end to end like this and measure the voltage? That one's a little bit higher, 6.5 volts, but still in the same range. All right. This one over here is even smaller. It's called a AAA battery. And the AAA battery, if we do it correctly, should basically measure the exact same thing. So we're going to, this wire's flopping around over here. We got them end to end over there, a little bit lower, 6.3 volts, but you get the idea, same range. And then finally, these little batteries, let me get them out here and put them out in front here. These little batteries are used in very small devices, right? Calculators and things like this. Each one of these is not 1.5 volts. Each one is 3 volts. So what I'll do is I'll just put one side on one and the other side here, and we'll see it's just a little bit over 3 volts. So if we stack 2 of them end to end just like this, we're stacking the mountains together. And what do we get? Just a little bit over 6 volts. So these 2 batteries stacked together is 6 volts. This gigantic battery here is also 6 volts. Why in the heck do we have all of these different sizes when the voltage is the same? What I'm going to do is tell you the punchline. All right? But then I have to prove to you that the punchline is correct. And we're going to prove it by building stuff. So let me tell you the punchline. We learned that we have Ohm's law that tells you how much current you will get when you put the voltage in and you get the resistance. So you think that if you put 6 volts into here, divided by whatever the resistance is, let's say it's a 10 ohm resistor, we already did that calculation, 6 divided by 10, we should get 0.6 of an amp. That's what we should get. But we also know that these 2 little batteries, when you add them together, is also 6 volts. So 6 divided by, if we do a 10 ohm resistor, we should get, again, 0.6 amps supplied by this. We can pick any of these others that we have used. This is about 6 volts. 6 divided by, again, 10 ohms, we should get the same thing, 0.6 amps. No matter what batteries we use, because the voltage is 6 volts, I've arranged them so they're all 6 volts. If I hook them up across this 10 ohm resistor, we expect to get exactly what we already got before. But we're not going to get exactly what we got before. What we're going to find out is that the physically large battery can generally keep up and supply the correct amount of current as predicted by Ohm's law. But the small batteries are going to try, but they're not going to be able to physically source the amount of electricity that Ohm's law is calculating that you should get. So again, this is the difference between theory and reality. Ohm's law will tell you what you should get. But in reality, inside this battery is a chemical reaction. And I don't feel like drawing a picture because I think it'll distract us from the main point. But in a chemistry class, we would draw the picture of what's inside of here, and I'll describe it. You have 2 conductors, which are separated by an insulator so they're not touching, and they're rolled up like a gigantic jelly roll inside of this thing. And there are chemicals inside of here that when you select the correct chemicals and the correct metals for the ribbons that are inside of here, they basically lose and gain electrons from the chemical reaction, and the electrons want to come out one terminal of the battery, go through, and then back into the other terminal. When the electrons get into the other terminal, they go back through the battery, and it's like going over and over again. But eventually, the reactants that are in here get depleted, and the chemical reaction cannot be sustained, and so the battery dies. That's what we say, that the battery is now dead, right? But even though this is 6 volts, And even though these two things are over here, this here is also 6 volts. There's a huge difference between them. The main difference is that inside of here, there's a large surface area of contact area for the chemical reaction to take place. Inside of here, it's constructed in the same way, or in a similar way, but there's a much smaller amount of surface area for this chemical reaction to happen. So we're going to learn that electric current is the flow of electrons per second. Because inside of this thing, there's a large surface area for a large amount of the chemical reaction to happen, it can physically supply the amount of electrons that Ohm's law says that should come out of it. But in here, there is not a large enough surface area to physically produce the amount of electrons that Ohm's law would predict. So even though these are both 6 volts, if I hook this up to a load and I hook this up to the same load, depending on what the load is, we might not get the correct amount of current that we predict ahead of time. So these physically larger batteries are going to be used in applications when we require a high current. And these small, tiny batteries are going to be used in applications when we don't require a large current. For instance, we might use this in a lantern to supply a very large amount of light. Or a car battery. You've seen car batteries, big rectangular thing. It's used to supply many, many amps to start an engine. It has to supply a large current to be able to function. But these little batteries, or these little batteries, they're not used to start a car. They might be used in your remote control or to power your calculator. The electronics in your calculator do not require much electric current, so it's able to function just fine. We have smaller batteries, even at the same voltage, to power devices that don't require a large electric current. We have to have physically large batteries to supply current in situations where we need very high or higher electric current. Now, that is the reason. And we can talk about the resistance of the batteries, and I'll talk about that a little bit later because, you can think about it different ways. But ultimately, that is the reason. But before I discuss it any further, I want to show you that what I'm saying is correct. And in order to show you, I've devised a little experiment, and I want to describe that to you right now. All right, what I want to do now is describe what we're going to do. Here, I have 5 different resistors. They're all 10 watts, which means they can take a lot of power without burning out. I just chose large ones to not run into any problems with burning anything up. The top one is 100 ohms, then we have 50 ohms, then we have 20 ohms, then we have 10 ohms, then we have 1 ohm. In general, what happens as you reduce the resistance? Well, according to Ohm's law, as the resistor gets smaller and smaller and smaller, the electric current goes up and up and up. So as we decrease the resistance in the circuit, if it's the only element in there, we expect the current to go higher and higher. What I'm telling you is that this physically large battery is going to be able to supply more current for a longer period of time than these little batteries because they're physically smaller. Even though in theory you would think they would do the same thing, they can't, because this one is just not large enough to supply the required amount of current. So what we're going to do is we're going to start off with only the 100 ohm resistor. And we're going to hook it up to a battery here, it's a 6-volt battery, and I have a table on the board that we're going to fill out. The first resistor in the list is 100 ohms, and we're going to, in theory, calculate what the current should be in this case. What should the current be? For 6 volts and 100 ohms, how do we find the current? According to Ohm's law, I is equal to V over R. You need to say that, 50 times. I is equal to V over R. I is equal to V over R. So 6 divided by 100, V over R, should be 0.06 amps, right? Now, we already said that 4 AAA batteries, right, which is what I was holding up right here, this is also about 6 volts. Yes, I know it's a little more than 6 volts, but I'm rounding to make the math a little easier. But this is supplying about 6 volts. So in theory, that's what the TH is in theory, it should supply also 0.06 amps. All right? What's going to happen when I change the resistance and cut the resistance in half? Well, it's going to be 6 divided by 50. And I'm going to get 0.12 amps as my theoretical current, 0.12 amps as well. The reason it's the same is because this is a 6-volt battery and this is 4 AAAs, which is also 6 volts. So across the same resistor, it's going to give you the same thing. Notice this current is exactly double this because I cut the resistor in half. What happens when I get to 20 ohms? 6 divided by 20, 0.3 amps. And over here, the exact thing, 0.3 amps. What happens when I get to 10 ohms? 6 divided by 10, 0.6 amps. And over here, 0.6 amps. What happens over here? 6 divided by 1 is 6 amps. And over here, what happens? It's going to be also 6 amps. I can tell you right now, these little AAA batteries are never going to be able to give you 6 amps. In fact, I'd be very surprised if this large battery could even do it, because you need a physically large battery to supply that many electrons per second to keep up with what Ohm's law is telling you should be happening. All right, so let's go ahead and do our little experiment. What we're going to do is use the 100 ohm resistor, and we're going to hook up this battery to it, and we're going to measure the electric current. Now, we have to learn how to measure current. The way I have this meter set up right now is as a voltmeter. So your meter, whatever meter you have, might be a little different, but you can see that to measure voltage with a V right here, you have to have it over here. To measure electric current, the electrons have to flow through the device. So you can't connect it here. You need to connect it over on the other terminal. If you're measuring current, you have to push the current through the device, so it has to be connected over here. So I'm going to put this back where it is, and what I need to do is I need to let the current flow directly through from the battery into the device there, into the measurement device, and so on. So what I'll do is I'll clip this battery, I'll connect it right here, and then it will come over and I will connect it to, I'm connecting it right here to my ammeter over here, measuring the electric current, right? And then it's going to go through the meter, and then the meter is going to come over here where I'm going to connect it back through the resistor again. So all I've done, I'm still connecting it directly through here. I'm connecting it through here, but the current is also flowing through my meter so that I can measure. And then I got to switch it over to amps right here. And so now I'm going to connect it to both sides. All right, so I'm going to connect this side of the battery here. I'm going to connect to the resistor right here, and I'm going to connect it over here. So all I've done is connect it in series where my meter is also in series with this resistor, and I will connect it right here. And I realize for this one, you have to press this button right here. This is trying to measure like AC current, so I need to like press the button until it says DC. So now the electric current's flowing through the resistor, the 100 ohm resistor, but also through the meter, and it's telling me 0.06 roughly amps, which is exactly what I calculated should happen. So I'm going to go over here and put 0.06 amps there. So Ohm's law is calculating what I should get in terms of the current. When I physically measure the current, that's exactly what I get, 0.06 amps. So let me disconnect that over here, and I'm just going to disconnect the large battery. I'm going to put it to the side, and now we're going to connect the small batteries to it, and we can use either these. Just to make it a little more interesting, let me grab the AA versions, which I think are a little bit fresher. I haven't used them at all. So here are the AAA batteries. Again, adds up to 6 volts. We already verified that and measured that. So what I'll do is I'll connect one side over here, right? And then the other side, all I've done was replace the battery, and we're going to measure over here what's going on. What do we get? 0.059 amps. 0.059. 0.059 amps, which is very close to 0.06, and the voltage of the batteries is not quite the same, so it's basically agreeing with theory perfectly. So I'm going to take this off before we drain our batteries. I don't want to drain the batteries. So when we are not asking the circuit to provide very much current, both the large battery and the small battery are able to keep up. There's enough surface area and chemical reaction in this little bitty battery to enable to supply this many amps through the circuit. And that's why it agreed with theory, and there was really no difference. So now what we're going to do is we're going to take this resistor out, which was 100 ohms. I'm going to put it aside so I don't accidentally use it. And I'm going to go down to my next resistor. This is half the resistance, which is going to double the current there. And this is a 50 ohm resistor. So we said for 50 ohms, we expect the current to exactly be doubled, 0.12 amps. So what I'll do is I'll connect this guy over here, and we'll see exactly what it measures right here. Let me connect it, like this. What do we have? 0.125 amps. That's what we're measuring, 0.125. So I'll put 0.125 amps. It's bingo, right on the money, able to supply the amount of current as requested by the circuit. Okay, so now we'll disconnect this. And now that we know what we're doing, it's going to go a lot faster. I don't have to explain every single thing. We're just going to connect these smaller batteries up to it and see what we get. Okay? Now we get 0.110. Let me make sure I have a good connection here, just to make sure there's no connection problem. 0.11. Let's round up. 0.111. Right? So we have 0.111 amps. This is still pretty close because it's 0.12, 0.111. It's a little bit lower, but it's actually pretty good. I would say that that's still agreeing with that. So even asking for double the current, it's able to keep up. So let me go ahead and take this apart. We're going to put this aside, and I'm going to take off this 50 ohm resistor. I'm going to put it aside, and now we're going to lower the resistance to 20 ohms. For 20 ohms, same voltage, we expect 0.3 amps to be able to be supplied. So I'm going to connect this here. I'm going to put the connect the battery right here, and I'm going to connect the other side of this resistor. This is a 20 ohm resistor here. And what does it give me? It gives me 0.306. So 0.306 is what this guy can supply, so they match exactly. All right, now I'm going to take the large battery off, put it aside. I'm going to grab the smaller battery right here, and we're going to see what it can supply. 0.3 amps, let's see, woo, that's a little different. It's not 0.3, 0.252. 0.252 amps. So clearly I'm going to disconnect it before I start draining the batteries down. I don't want to influence our experiment. But you can see that right here, somewhere between here and here is when the break happened. What's going on here is this physically large battery is able to supply enough current in accordance with Ohm's law. It's bingo, right on the money. But the physically smaller battery, even at the same voltage, is really unable to do so. It's not able to keep up, and you can start to see it break with what the theoretical value is. But let's keep going, because I have more resistors, and I bought them, and I want to see how far we can take it. So we're going to go to 10 ohms here. And I'm going to take this one away, and we'll get the large battery, and let's see what the battery is able to supply here. The theoretical value at 10 ohms should be 0.6 amps. It's starting to actually be quite a bit of current. And what we get here, 0.562 amps. So that's pretty respectable, but not quite 0.6, 0.562 amps. But it's able to supply, and notice it's going down a little bit here, but it's able to supply pretty close, I would say, to the theoretical value. Let's go over here and connect the smaller battery. And if our theory is correct, this thing is not going to be able to keep up basically at all with this. 0.418. I'm going to disconnect it so we don't drain anything. 0.418. So the small battery was able to provide 0.418. Now you might say, well, wait, what's going on? I thought he said there was a limit here and this battery can't go above the limit, but it's above this one right here. What's going on? What I'm saying is the resistance that's connected externally is trying to, quote, ask for a certain amount of current in accordance with Ohm's law. And it's able to get as close as it can to that, but what's happening is as a percentage, it can't get as close as it should get. Notice the percent between here and here is pretty close. The percent difference, if you were to calculate it between here and here, is quite large. So the percent error in what you're able to achieve with a smaller battery is just not going to be able to keep up. It's going to get as close as it can. What's going to happen? It's going to drain faster and faster and faster as you start asking for that current, because the chemical reaction will deplete faster. All right, let's go down and do our last resistor, which is a single 1 ohm, one tiny little ohm resistance. And so we're going to do that one, and we're going to find out that basically neither one of these batteries is really going to be able to keep up with it. 6 amps of current is a very dangerous amount of current. You have to be careful with this kind of thing. Let's see what it can supply. So here we have 2.8 amps, right? 2.8 amps. So I'll write it down. 2.8. It's going down. Notice it's going down, 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 because it's draining the battery. So I'm going to go ahead and put it, I didn't see the exact numbers. I'm going to call it 2.8 amps, roughly speaking. And let's see, let's disconnect this one and connect the small battery to it right here and see what this thing does. And I have to be really fast because it's going to drain this super, super, super fast. So when I connect it, 1.31, notice it's going down, 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 down because it's draining the battery. I'm going to call it 1.31 amps. So 1.31 amps. Now notice the percent difference, right? If you look at the percentage between this and this, obviously it's not able to get proportionally as close to the theoretical value as was able to get here. So it's not like there's this like hard barrier beyond which the batteries can't, well, there is always a physical barrier, but what I'm trying to say is the point of this experiment wasn't trying to show you, aha, there's a physical barrier beyond which these batteries can't go. What I'm saying is that as you hook a load of a lower and lower resistance, then the battery is going to try to push as much current out as it can to satisfy Ohm's law with that load. But what happens is that as it asks for more and more and more current, it can't keep up with what is demanded. So these small batteries, even though they have the same voltage, a 6-volt source, they cannot supply a high enough current. And notice that the current was literally bleeding down the whole time because you're literally depleting the chemical reaction in the process. And so it's not able to keep up. The large battery was not only able to keep, notice the breakpoint was here for this battery, it was able to keep up longer, but also even when it started to diverge, notice this is pretty close still, but when we got it to here is when we saw a huge divergence. But even this is almost able to supply half the current requested. This is not even close. So the larger batteries can get closer to supplying the theoretical amount of current for a longer period of time. And of course, they'll take longer to deplete as well because there's more reactants inside. And so they can not only do that, but they can supply the current for a longer period of time. So you use large batteries when you need a higher current source, or if you just need to supply current for a longer period of time. Physically larger battery can supply current for a longer period of time. You use these tiny batteries for very low current applications like a remote control. A remote control in a television might take a milliamp or even a microamp. It's just not going to require very many electrons to power those little transistors inside your remote control. So a small battery is sufficient, and you can even get away with these very tiny batteries for these very low current applications. Now there's one more thing I'm going to talk about here that usually is we save it for a little bit later when we get in more detail with circuits. But another way of thinking about this, I've described it in terms of how many electrons it can supply. But actually, I don't want to get into it now because it's a little bit too early, but if you draw the kind of the circuit equivalent of an actual battery, you can model it as a voltage source, but also with some internal resistance. In other words, this device has physical objects inside of it that have resistance. And this device, in the chemistry, the chemical reaction, and also the wrapped foil inside of it has resistance as well. Which one of these things do you think is going to have the bigger resistance? Actually, it's going to be this one. Smaller objects have bigger resistance because the electrons just have to cram through a smaller place to go anywhere. This thing has a lower resistance. So some of this effect can be described in terms of the resistance of the batteries. I'm actually going to do a lesson later on that process, but we have to get a little farther beyond Ohm's law to understand how that predicts what we're doing here. But for now, I just want to say that Ohm's law is a linear relationship between the voltage and the current given a resistor as the load, which is a linear circuit element, right? Different than transistors and diodes we'll get to later, which are non-linear, right? And Ohm's law calculates the theory, the theoretical. The power supply that I'm using over here can supply enough current. It can adjust itself to supply enough current depending on whatever is asked of it, because it's coming from the wall electricity. And there's a limit to that as well. I can't have a megawatt of power coming out of this thing. But for anything I'm doing on the bench, it's going to be able to supply enough current in accordance with Ohm's law. Even though this is 6 volts and this is 6 volts, the theoretical currents that are requested are not always able to be honored, for lack of a better word. So we have to ask ourselves the question, okay, if it's true that Ohm's law is always true, then what's actually going on? If I'm supplying a 6 volts as a source and I'm doing it across a 1 ohm resistor, right? Then I'm calculating 6 amps. This is what Ohm's law tells me, but I'm not actually getting that much current. Doesn't that mean Ohm's law is violated? Doesn't that mean Ohm's law doesn't work sometimes? The answer is no. What's actually happening is if I were to measure the voltage on these terminals without anything connected, I'm going to get the 6 volts. But if I'm trying to demand too much current of it and I measure the voltage while that's happening, I'm going to get something less than 6 volts. In other words, the voltage will be drooped or drop on this thing when it's unable to supply the correct amount of current. I want to show you that right now. I think the simplest way to show you is to reconnect the 6 volt battery to it. So what I'm going to do is connect this here, and we've got going through our meter over there, right? And we're going to verify again what's going on. We're only getting a little bit less than the 3 volts or the 6 volts that we were getting, a little bit less than 3 volts. So what I'm going to do now is actually disconnect the probe so I can actually measure the voltage while I'm going to reconnect the circuit, but without the meter in place. And I'm also going to go here. Notice I told you I had to connect it over here to measure current. I'm going to go back to measuring voltage. I want to show you what the voltage on this battery is when it's in operation. So I'm going to put this up over here, right? And then what I want to do is I want to hook this thing up. So I don't think I'm going to need this. I think all I really need is to hook it across the battery, right? So we're doing the same thing. I'm just hooking it across, and we already know it's about 2, almost 3 amps, something like that. And now what I'm going to do is, while this thing is in operation, actually let me disconnect it. While there is no current flowing, what is the voltage across here? The voltage is, if we look up, whoop, we got to switch it over back to voltage. So we're going to go to voltage. What is the voltage? The open circuit voltage when nothing has happened. Notice it's already a little bit drained because I've been using it a lot to supply a lot of current, but it's at 6.2 volts. But when I'm unable to supply the current, right, and I'm now asking, I'm getting about 3 amps flowing through that. What is the voltage right now? The voltage is not 6 volts anymore. It's dropped to 4.3 volts, and it's dropping even more. So let me disconnect that. Let me explain that. When you have a battery not connected to anything, you have what's called the open circuit voltage. We saw that it was a little bit over 6 volts. We were using the battery a little bit, so originally it was 6.4, but then it was just 6.2. When I'm asking the battery, give me 6 amps, and it's like, I can't, this is all I can give you. You think it's violating Ohm's law because it should give you this, but it's not. It's giving you something lower, and what happens is the voltage across the battery terminals also drops because it physically can't keep up. And you can also explain this in terms of the internal resistance of the battery. In a future lesson, I will draw that picture for you and show it to you, but it's sufficient just to say that when the battery can't keep up, Ohm's law is never violated. The 6 volts that you thought you had, you didn't really have it, because as soon as you start asking too much current of it, then the chemistry just can't keep up inside. The battery voltage drops, and that's why it can't supply the correct amount of current. Now, since we're talking about voltage, I can't end the lesson without talking a little bit about AC versus DC. Direct current, alternating current. This battery, all of these batteries, and including the supply that I'm using here, are what's called direct current. And if I were to use an analogy, if you look at this piece of string here with these lines on it, these little dots are meant to be the electrons in a circuit. And so if I use my imagination and say, okay, it's connected like this, direct current is something that flows like this. It comes out of one terminal and it just goes and goes one direction over and over and over again, and it just keeps going. The voltage is only in one direction, and the electrons are only going one way over and over and over and over again. Direct current. But in alternating current, what's happening is things are alternating direction. What happens is the current might flow out of one terminal of the battery for a little bit and then switch directions and then start going the other direction like this, and then stop and then switch directions and then come back the other direction like this and then stop and then go back the other way and then go back the other way, and it alternates back and forth, back and forth, back and forth, back and forth, back and forth over and over again forever. Now in the United States, the frequency of the switching back and forth is 60 hertz, which is the switching happens 60 times every second, right? But in other countries, it's 50 hertz, in other countries, it's different frequencies, and it's related to how the electricity is generated at the power plants. Basically, what you have is some sort of steam generator, usually from coal or from nuclear, and the steam is turning a generator. The generator is a coil of wire in a magnetic field, and it's rotating. And because of the rotation, you get the backwards and forward motion of the electrons. I'm not going to get into it here, but it's because of the rotational motion of the generators in the large power plants. That's really why we have AC current. Also, it's much more efficient to transmit AC electricity over long distances. If you try to do it with DC, you'll have a lot of losses due to heat. It's not very practical. So we have the generation and transmission in terms of AC. When we get it down into our walls, we also are using AC coming right out of the walls, but our portable devices like our batteries are all what we call DC, only one direction of the voltage and of the current flow. I hope you've enjoyed this deeper dive into the concept of voltage. I really wanted to focus on voltage, of course using Ohm's law as well. Next lesson will be on a little deeper dive look at current, and then a little deeper dive looking at resistance, and then we'll get into more complex circuits. So I hope you've enjoyed this. Please drop me a note, let me know what you think. Follow me on to the next one.
Learn anything at mathandscience.com.